Hello everyone. In this video, I am going to discuss about a new phenomena that is luminescence. In the previous video, we have talked about optical absorption. So let's discuss what luminescence is. So here you can see when we talk about that there is a generation of electron hole pair in a semiconductor, the first phenomenon is absorption. So when absorption is there, on absorption, there is a generation of electron hole pair in a semiconductor. So with that, what happens? Carriers are excited into higher impurity levels from which they fall to equilibrium states. So in the previous video on absorption, what we have discussed and that there is absorption, and this is your conduction band, this is your valence band, and your electron moves from here on absorption of energy, photon, electron move from valence band to conduction band. So when it comes back, what happens? It can be give light depending upon the material. So when we talk about semiconductor, and if we are interested in light emission, then many semiconductors are well suited of light emission. And in particular, if we talk about then compound semiconductor with direct band gaps. So there is direct band gaps in compound semiconductors. So when they have recombination back, then there is some generation of light. So when photon is there, this generation is there, they move towards valence band to conduction band, and then when they came back, they will accompany some light depending upon what kind of material it is. So if particularly we are talking about compound semiconductors or direct band gap semiconductors, they will definitely give some sort of light. So when we talk about the basis of excitation mechanisms, then we have photon absorption, and other one is high energy electron bombardment. So when photon absorption is there, then the light which comes, that is in the form of photoluminescence. And when you talk about high energy bombardment, then cathodoluminescence is there. So when other thing is also possible, that when you introduce current into the sample, then that gives you electroluminescence. So two mechanisms are there. These two particulars are same, but little bit different. So they are given cathodoluminescence and electroluminescence, and this is accompanied with the light of photon of particular energy. So that is photon absorption. Now, photoluminescence. The simplest example of light emission from a semiconductor occurs for direct excitation and recombination of an electron hole pair as depicted in figure. So this is the simplest example. So I will be showing you this. So here you can see. So it is actually accompanied in different steps. I will be discussing them later on, but just for idea, photon absorption, this electron moved on to this, it lose some energy, came back to this particular level, being trapped at this particular level, again given some energy, so it go back to D, level D or conduction band once again, and later on it come back. So these are the 5 different steps. So in the previous discussion, what we have discussed, that they will fall directly to the valence band, but right now there is a trap level because you are adding some impurity. Because of that, your electron will be trapped here and it will re-excited to the level in the conduction band. So let's discuss this once again. So direct excitation and recombination of electron hole pair as already shown to you in the figure. Now, if your recombination occurs directly rather via defect level, band gap light is given off in the process. Otherwise, what happens when you are having steady state excitation? Recombination of electron hole pairs occur at same rate as the generation, as one photon is emitted from for each photon absorbed. One photon is emitted, one is absorbed. So these are the two different things. One is steady state, another is recombination. Now, when we talk about direct recombination, that means there is no excitation, re-excitation, or your electron is being trapped. So this is called direct recombination. So in this, we expect the process to be fast. And in the meantime, lifetime of electron hole pair is usually on the order of 10 raised to minus 8 second or less. That means your system gives this much time before your electron hole pair is going to recombine. So when you talk about emission of photons, so it will stops within this much seconds after the excitation is turned off. So you turn off the excitation, immediately your photon stops. That is 10 raised to minus 8 seconds. So you are witnessing this fast or rapid luminescence process. So it is sometimes referred as fluorescence. So in some materials, however, what we see that emission continues for periods up to seconds or minutes after the excitation is removed. So how it is happening? Because it is having a trapped level. So your system is actually re-exciting itself after gaining some energy. So the slow processes are called phosphofluorescence and the materials are called phosphors. So this is the difference between these two, that you are having, on the one hand, you are having this particular fluorescence that is for a very small duration. And if it is for a prolonged duration, then it is called phosphorence or phosphors, and materials are called phosphors. So let's discuss this now in detail. So you provide a particular energy, electron will be excited. Now it enters into this particular lattice. So in this, it will lose some of the energy in the form of what we can say your not radiations, it is losing energy and due to scattering events. Then it will come back from here to here, it will radiate some energy or maybe not. Then it is being trapped at this particular level, ET, and it is re-excited. So once it is re-excited, it will again enter into the conduction band, but energy is not enough so that it can be in this particular level. It will remain at this particular level, and after staying at this level for a certain time, it will come back and it is incorporated by radiation of energy. So the duration is being decided by mean time, that how much time your electron is going to spend in the conduction band and how much time it can be re-excited. So that's a rather important thing. So in this picture, we have this particular being discussion or figure being discussed, that it incomplete by 5 steps, 1, 2, 3, 4, and 5. So first is excitation. Second is it is losing some energy in the form of scattering events inside the lattice. It is falling to this particular level, and here it is re-excited, and again this is step D, C and D, and then it lose energy accompanying some radiations of frequency h nu, and it is coming back to the this. So this entire process keeps on until and unless we are having this particular excitation. So you remove the excitation, this process is going to be ceased after some time. So this is the example we are talking about. So it's a slow process. The material contains a defect level due to an impurity. The trapped level which I'm talking about in the previous slide, here you can see this is because of impurities, this thing. This thing is about impurities. Here you can see this is impurity level being introduced. So now you will know what is the impact of impurities, adding impurities. So this material contains an defect level in the band gap, which has strong tendency to temporarily capture electrons from the conduction band. So the electron directly do not move from valence conduction band to valence band. In between, there is some trap. So the first thing is creating of electron hole pair. Then second is the excitation, electron gives off energy to the lattice. Third is trapped and remains trapped. It is thermally re-excited. And fifth one is recombination. And it is accompanied by giving a photon of certain energy, h nu 2. So the delay time between the excitation and recombination can be relatively long if the probability of thermal re-excitation from the trap is small. So if it is what we can say, if this probability of thermal re-excitation from the trap is small, what will happen? The delay time between excitation and recombination can be relatively long, and this gives you certain phenomena. Now, if you talk about longer delay, then electron is re-trapped several times before recombination. So before it is moving from this valence band, conduction band to valence band, so it will be trapped several times before it finally comes down to valence band. So if the trapping probability is greater than the probability of recombination, probability of trapping is greater than probability of recombination, electron makes several trips. That means if this is a trapping level, it will be here for so much time if this probability of trapping is greater than probability of recombination. So if such a material, the emission of fluorescent light persists for a relatively long time after the excitation is removed. So in that material, what will happen? There is emission of phosphorescent light, and this gives you relatively long time after the excitation is being removed. So the color of light by phosphorus, such as zinc sulfide, depends primarily on the impurities present, since many radiative transitions involve impurity levels within band gap. So if you're adding impurity levels within band gap, so this is your band gap, here you are adding impurity levels. So this gives you the particular levels. So this actually decides what kind of color you are going to obtain. So the color useful in fabrication of color television screen. So when you talk about color TV, now we don't talk about this. The time this book is being there, then used to be there. Right now we are having LCDs and LEDs, or maybe some projection screens. But you should know what is the phenomena behind it. So the most common example of photoluminescence is fluorescent lamp, which we commonly use. So that's all. Thank you very much. I hope you understood the concept of luminescence. In luminescence, this is the important thing that need to be there, that you should know that whenever there is a recombination from this level to this level, there is some energy. But before recombination, there will be certain thermal re-excitations in luminescence. So the more the thermal re-excitations, and the duration of the luminescence will be longer. So thank you very much. See you in the next class with new topic. Till then, goodbye.